right now I'm a software engineer at Apple. I live in Seattle. I work out of Seattle. If I'm trying to impress people, I tell them I work on CarPlay. If I'm not trying to impress you, I work on Siri. The truth of the matter is I work on integrating Siri into CarPlay. So, you know, Siri, right now we're working on the next generation of CarPlay, making sure that Siri is happily integrating that, as well as a whole bunch of other top secret things that I will never tell you until it's released.
Do you get a free car with it?
Yes. Not a free car, I get a company car, though. One nice perk on my thing is that Apple has a fleet of about 12 cars, and I can just check them out wherever. I permanently drive a company car, and some of them are nice. We have some Porsches, we have some Audis, we have some Minis, for development reasons.
Yeah.
It's funny too. All right, so about a year ago, I went through what you could call a midlife crisis, where I tried to figure out like, who am I, what's going on. But instead of buying a fast new sports car or cheating on my wife, like a lot of people with midlife crises, I decided to drop about $7,000 on astrophotography equipment.
But it is red.
It is red, so there you go. It's top, it's sleek. So right there is my setup. It's a super awesome telescope with a super awesome camera and a super awesome mount that literally will just track whatever I tell it. It's fully programmable. It was kind of a dumb decision because I live in Seattle, like the heart of it. Not only am I fighting this big, massive city light dome, it's also cloudy about 90% of the days. So why I decided to drop $7,000 on this hobby, I don't know. My wife doesn't know. But I've absolutely loved it. I've enjoyed it. These are some pictures I've been able to take. You have the Veil Nebula there.
Wow.
The really cool nebula there.
Very cool.
I have an Instagram. It's @Drawing. I post stuff when I can because I live in Seattle. I only maybe take 4 pictures a year. But if you want to see the 4 pictures a year I take, you'll see it. But here's the thing. Most of the stuff I've been taking pictures of is galaxies or space dust, glowing space dust. And after a while, I got tired of taking pictures. Not tired, but I wanted to branch out to taking pictures of planets. By the way, if anyone ever wants to chat about this stuff, let me know. I'm always happy to nerd out about taking pictures of space dust. But the problem is you need to buy all sorts of specialized equipment to take pictures of planets. You can't use the same equipment you use to take pictures of the galaxy and nebula. So I went out, and this is the telescope I bought. It's a Celestron Edge HD, and I bought a specialized camera. The focal length for all you photography nerds out there, it's about 2032 f10, so it's slow and long, meaning it's super, super zoomed in. Specifically, just to give you an idea of what the telescope can do, it's about 75 times the zoom of the telephoto lens on the iPhone. So, it's lots and lots of magnification, right? Now, this is a picture of this is not my picture, I wish it was. This is a picture taken by a guy named in Arizona, Andrew McCarthy, and I show you this because I want to give you an idea of what awesome people who know how to take awesome pictures of planets can do, right? This is one of the ideal things that you can do. I took my fancy camera and I put in my fancy telescope and I snapped a picture and I loaded up in Photoshop. I did all the traditional things you do in Photoshop to develop it and process it, and this is what I came out with. Wow. I mean, yeah, right? Thank you.
See the rings.
Yeah.
What year was it that they finally
got
got
right.
the rings? So
Exactly,
it was
right? I mean, I'm not ready to call myself Galileo yet, but I'm getting there, right? So this is what I wanted. This is what I got. And this. Now, to be fair, no one would ever actually take a picture of a planet the way you described it. You just put your camera in and take a single frame, and you do that because it doesn't work. It turns out like that. It looks like crap. But I wanted to show you, just to give you a perspective of what we're starting with. This is, if you just want to naively stick a camera in a telescope and snap a photo and edit it, this is what you'll come up with. And it's not great. And why is it not great? Let's talk something a little bit about planets. Planets are tiny. They are the smallest things in the sky. You guys see that little speck right here? So this is the size of Saturn compared to the size of the full moon. Next time you're looking at the full moon, imagine this tiny little speck, and that is the size of Saturn compared to the full moon. It is tiny. It's planets are some of the tiniest things you can take pictures of. The moon in the sky, like obviously not in real life, and just like that from our perspective here on Earth, the moon is about 100 times bigger than Saturn by diameter, and about 9,200 times bigger than Saturn by area. Saturn is so tiny that if you took that super telephoto lens on the brand new iPhone 15 Pro and you zoomed all the way, you pointed it up, it wouldn't even fill a single pixel. That's how tiny these planets are. In my super telescope setup that's, that I just showed you, it only takes about 80 pixels. Like that's just how tiny this thing is. And for those of you who are wondering, like, this doesn't make sense. I've seen Saturn next to the moon. It's really bright. It looks like a super big, bright star. Now, this is the weird thing about planets, is they're bright. They are the smallest and the brightest things in the solar system. But if you cleared out all the light, put a filter and just get the detail, it would just be this tiny little thing you have to capture a picture of. So we get this weird question of, how do you take a picture of something this small and this tiny? Well, you run into problems, and these are the big problems you run into. The first is it is literally impossible to achieve stable focus. So you're going through this atmosphere, you have this tiny thing, and the atmosphere is, they call it turbulence. Have you ever lit a fire or gone to the desert and you've seen mirage, how the air gets kind of wavy and shimmery? Well, any heat will do that in the atmosphere. When you're dealing with something this small, you get, no matter how cold it is, no matter how stable it is, you're going to get this shimmer effect, which is going to cause your focus to go in and out. So that's the first problem you have to face. The second problem you have to face is that even if you, somehow get over that atmospheric shimmering, you're not ever going to achieve perfect focus because the atmosphere, all that air is going to act like a lens. It's going to act like a second lens on top of your telescope, which is going to cause, which is going to be impossible to get that perfect, clear focus you want. And the third thing is that lens is going to have a prism effect where the red wavelength will travel, I can't remember if it's faster or slower, but one of them, than the green wavelength, than the blue wavelength, so you'll get all this crazy color fringing at the edges. And so these are, if you want to take a clear picture of Saturn, you have to get over these issues. Now here's the nice thing, is there actually is software you can download to get this. The problem is the software is usually written by scientists, folks, who research this stuff, so it's terrible software to use. The bigger issue is it's all Windows only. A lot of it hasn't been updated in years. The most popular package right now, if you go onto any YouTube tutorial on this or search anything, is something called Registax. It was last updated in 2011. Literally, the most popular software to do this hasn't been updated in 13 years. There is newer stuff with newer algorithms, but at the end of the day, it all runs in Windows. And not only does it run in Windows, it doesn't play well with things like Wine or Windows emulation or even virtual machines. I struggle to get this stuff going. Literally, if you are a Mac guy and you're running Apple Silicon hardware, which breaks all the Windows emulation stuff, then you cannot do any planetary processing on your Mac. And the advice that you get is, it's so funny. There's all these questions of how can I process my pictures of planets on a Mac? And the answer is always, buy a Windows machine, buy a Windows machine. There just isn't a good way to do this. And I learned that the hard way. But here's the thing. I work for Apple. I'm a software engineer, kind of. I pretend to be. Why not just write my own thing? And that's what I ended up doing. I wrote this software called Planet Stacker X, which basically takes all the functionality of some of these things. And this is something I've been working on for about 4 or 5 months yet. It's still very much a work in process. I am actively developing. I'm going to be, showing you guys the code here, showing you this. The UI looks like crap because it's still under development. The code isn't fleshed out. There's still lots of features I'm missing. This is active development, but you know what? I'm going to basically show you how I was able to solve those problems and what algorithms I had to implement in order to be able to do this. So,
Drew, can
yeah?
I interrupt for just a
Yeah.
second? For those of you that did not get any pizza, there's still about 3 slices left if you'd like some. That's it.
So if anyone has any questions on any of this, just raise your hand.
Swift UI?
Yep, it's all Swift UI.
Nice.
It's all native.
This at all?
What?
Have you released
I
this at all?
can't. I work for Apple. They won't let me.
I'll just send it to me. I'll say I wrote it.
There you go. Or, ultimate developer, I can't remember my wife's name, she released it. No, but like, this is the sad thing, is I work for Apple, and Apple has a very strict no tolerance. Like, I can develop software for personal use, I just can't distribute it in any way, shape, or form. I can't open source it, I can't email it to other Apple employees, I can't do anything. If anyone here has ever talked to Dave DeLong about his app, like, it's a thing. But yeah, it's a thing. Anyway, this is all native macOS libraries, natively written SwiftUI, the Apple Vision Framework, the CoreImage. The first version of it, I actually implemented all the core algorithms myself. I wrote my own little tiny image processing software, and it worked great. And then I realized CoreImage is probably better, and so I converted it to CoreImage. But anyway, so I'm going to give a really brief tutorial on CoreImage, just because this is built on CoreImage. And there's really only two things you need to understand about how CoreImage works. First of all, is what is CoreImage? It's a really simple library in concept and abstraction. The basic idea of it is you have an image goes into a filter, image comes out. That's literally it. And they have tons of all these built-in filters. So in this code example you see right here, this is just a really simple example of how to blur a UI image. You literally choose your filter. In this case, you can choose a Gaussian blur. You put your input image, you choose your radius, and then you get your output image and create an image out of that, and boom, you now have blurred your photo. That's an example of what this little code sample does. So everything I write, it's basically taking CoreImage filters and putting them through, or a lot of times, I write my own CoreImage filter. So this is the other concept you have to understand, is CoreImage allows you to write your custom filters if you don't want to use any of the built-in filters. And that'll work in something. Now, if anyone here is expecting Swift, I'm sorry, this is metal. This is a shader. And the way a custom CoreImage filter works is basically you create a metal function and it works on a pixel basis. So for every single pixel of the image, you're given an input position, an input image where you can sample it, and then you return an output pixel. And so in this case, this would be a really simple custom CoreImage filter that literally just takes in the input image, you get the coordinate, you sample it, and then when we return, we just return the red channel, and then you get that because we're just returning back the red channel here. So these are the two basic things that I did. Some filters will work on them. Some are going to be a combination of built-in filters. Some of it will be custom filters I had to write. Okay. Now, going back to the algorithm. So the first issue we have to solve in taking pictures of planets is atmospheric turbulence. And actually, I have a video here I was going to show that I forgot to show. So let me show this video so you understand it. So if you play this video, notice how it shimmers in and out. This is a video of Jupiter I took. And you can kind of see that, I don't know if you can tell from the screen, it's all more obvious on the computer screen, but basically it's shimmering. Now that's what we're trying to solve. The heat of the atmosphere is causing our focus to shimmer. We literally cannot achieve stable focus. How do we solve it? So that's the first problem we're solving. And you use an algorithm called key imaging. So basically, you don't take a single photo, you take as many as you can. You take a video. And the nice thing about the planets is they're so incredibly bright that you can take really high resolution video really easily. You capture the video, get as many frames as possible, you run analysis on the video, and you extract the n number of frames with the best focus. So you literally, like, every frame of this video, which one's the most sharp? Which one's the most clear? And you might take the top 10% of in-focus videos, or the top in-focus frames, or the top 20%, or the top 40%. And then you average all of these in-focus frames together to form a single image. And you kind of see that you can go from 1 frame to 4 frames, 16 frames, and the more frames you gather that are in focus and the image together, eventually you get a nicer, more crisper, clearer image. So let's take a look to see what this looks like in code. I'm going to go ahead and show you my Xcode. Here's my Xcode. Let's go ahead and, actually I'm going to share my screen instead. Let me share my full screen. That way you can see both the code and the thing when you run the app. It succeeded. Okay, so here's my app, Planet Stacker X. First of all, what we're going to do is we're going to take a picture of Saturn that I photographed last, oh geez, when was it? It was, when conjunction was it? I think it was about September.
September 11th?
Oh, what was the timestamp? There you go. Okay, so we're loading it.
And it's literally a video file.
It's literally a video file. It's an AVI file. It's raw.
Nice.
There's no compression involved, so it's literally just the raw frames, which means these videos get really big really fast. I think, but yeah. So it's a raw AVI, raw dump from my camera. That's literally just the raw frames. So here, let's just watch the video. So this is the video I see. So the first thing you'll notice is it's jumping around, it's moving around the frame. And that is because we're so zoomed in on the super small target, slightest jitters will cause it to go in and out. Like even me walking around the telescope, my kids jumping up and down on the concrete, they will cause these jitters. So the first thing we have to do is we have to align it. Now we have a video which is perfectly aligned. But you can still see that atmospheric turbulence causing it to shimmer. That's the heat wave effect I was telling you guys about. So
What algorithm are you using to perform the alignment?
I'll jump into the code in a second,
Oh, okay.
for this, but literally just Apple Vision framework, they have what they call a registration function where they'll run analysis and they'll align it. So the next thing we do is we align it. The next thing we do is we run edge analysis, and that basically kind of looks like this. So these are the edges that it detects. And what we do is the more edges we detect, the sharper the focus. The less images we detect, the less clear the focus is. And you'll notice right here that we have this nice little thing called frame order. And when I move that to sharpness, this then organizes the frames by how many edges they have, how few edges they have. So, you can see like at the beginning of the video, nice and focused because, it's sharp. But at the end of the video, the focus goes out because we don't have as many edges. So then we have to choose a point where, how many of these focus frames have we got? And here's the thing, there's no stopping point. There's no clear point where it's in focus and it's out of focus. It's going to be a gradual curve. So you just kind of choose. Just going to show you what this looks like with edge analysis. Few edges, lots of edges. Few edges, lots of edges. Out of focus, in focus. I'll probably just choose something around the middle, just because it's nice. So we then put in 50%. Here, let me go. We'll put in 50% here. That's going to stack 50% of the frames. We'll hit the stack button. And now it's running that alignment. It's choosing just the top 50% of frames in focus, and it's averaging them all out together, and we will see what we get. Boom. A lot better, right? It's getting there. Not perfect. Not amazing. There's still stuff we have to do here. But you know what? It's better. Okay, so let's jump into the code now. So the main code here, we have the stack function that I put under here. Stack. Sorry, it's in here. Right. Yeah. So basically, first of all, actually, the first thing I'm going to show you is this. I'm going to show you a couple different things. First of all, I'm going to show you quality. So how do we figure out the quality of it? So first of all, we make grayscale. This is going to be a built-in CoreImage filter that just takes the image and makes it grayscale, right? That way we don't, if the red channel, blue channel, none of that stuff is going to matter as much. We get the edges. Luckily, CoreImage has a built-in filter called Edge Finder, which it literally will just produce an edged image. We then run a threshold filter. This is another built-in CoreImage filter, which basically does a threshold. And what a threshold means is it makes it bicolor, only black and white. So you choose a threshold, like say 50%. Any color that's 50% gray or above, it makes white, and everything else it makes black. And that will just get really crisp, clear images. We calculate the average of the frame. This is another built-in CoreImage filter, which will just return a single value. What's the average of that frame? And then we assign a quality score. And that is how we determine what is the quality, what is the sharpness of that frame.
So that's just a way for you to count the edges that we protect.
Yes, yeah. So rather than doing an actual edge count, and you can do that, and I actually do have a branch which does that, it's slow.
Yeah.
And I didn't notice a huge difference in quality between just doing straight average versus an actual edge count. If I ever do actually release this thing, I'll probably run more analysis and try to determine. For the alignment part that I was showing you, this is basically what it looks like. First of all, we run that threshold on there, just because that just makes the algorithm, it's just easier for the algorithms, and they don't have to deal with all that color and grayness and stuff like that. You can just give it a nice, sharp thresholded image. This is Apple Vision. You make an Apple Vision request. It has this object called, it's literally just these 3 line of codes. It has this thing called the registration request. You give it 2 images, you perform it, and then it will give you a translation of, how far do you translate image B to line with image A? And you transform it. For the stacking, the averaging we do is, I ended up creating really simple custom CoreImage filters. So we have one called add. This literally what it does, it takes in 2 images, an input image and a background image, and it just literally adds the RGB channels together and returns it. So and then I created one that's divide, that you just basically give it a number, and it just divides that. And our average stacking, literally what it does is I just literally keep adding image after image after image after image. Then when I'm ready to render, I run divide, and boom, we've averaged. And that will give us this image. Any questions about that before I go on to the next step of the algorithm?
Is there not a built-in addition filter?
There's a composition one, but the problem with it is it also includes the alpha channel, and that messes things up.
So if you add a whole bunch of images together, and you're accumulating them to a single float per pixel, you end out losing some precision on those pixels. If you,
Yeah, I'm glad you brought that up because this was actually something I ran into. There's this concept of color spaces, and basically, how do you represent a pixel? Do you do a 0 through 1? Do you do 0 through 255? Do you do whatever? And basically, when I first ran this, I actually got this bug where I'd get these weird black specks, peppered throughout the image. And what ended up happening is I was using the default CoreImage color space, which didn't give me enough precision to add everything together. So I had to change my color space to one that gave me more precision. I can't talk. Precision.
because you accumulate first and then you divide by the number of images.
Yeah.
Something maybe worth trying is accumulating like pairs of image and then pairs of pairs and then.
Yeah, I thought about doing it that way, where basically I did a rolling average. That's what you're suggesting. And my first version of that did it that way, but I got a little bit better performance just doing it this way.
Yeah.
So
Yeah, the straight average would certainly be faster to calculate,
yeah.
as long as you can get away with doing the accumulation all on a per pixel basis.
Which color
Very
space are you
interesting.
using?
Float 64. Okay.
Yeah, as long as you're adding less than like 1,000 images, you're probably going to be okay accumulating into a float 64. Huh.
Okay. All right, let me go back to the presentation. Any other questions before I go into the next thing we got to solve? I think.
You lost your screen share.
Keynote back. Okay. I want to tell you a story about the Hubble. You guys probably know the story, but I love the story. It's my favorite story. So the Hubble, they spent how many billions on it? I don't know, a lot. It was this big, huge thing. It took all this political lobbying and all this effort to get launched to space. They launched into space, and they pointed to M100 galaxy, and they expected this image on the right. But instead, they got this image on the left. It was a blurry mess. This big, huge project that they spent all this money, and all the libertarians came out and said, yeah, government can't do anything. And, it was a thing. And so those NASA scientists had to sit down, and they said, how can we correct these images from the Hubble? How can we get usable data out of here? And eventually what happened was they sent a bunch of people in space with a giant contact lens, basically, and put it on there. What happened is the mirror was up. The mirror had a small, tiny, it was just like a few microns thick flaw in it. But that few microns flaw in the mirror of the Hubble caused these blurry images. And like I said, they sent people up into space with basically a giant contact lens that they bolted onto it to get the clear images. But before they did that, they had to figure out how to get usable data. So NASA actually came up with a sharpening algorithm called the ATRO wavelet transformation algorithm. Blah. with holes. Another name for it, for anyone who's ever taken imaging processing, another name for it would be the stationary wavelet transform. And this is how this works. I love this algorithm, by the way. This thing I think is so interesting and crazy. Basically, you take a smoothing function. For those of, there's lots of smoothing functions out there in signal analysis. You have things like B-splines, linear interpolation, blah, blah, blah. Forget all that. Let's just pretend, for an example, you just take averaging. You have a group of pixels, you average them together. That creates, for every single pixel, by the way, this is a 50 by 50 pixelated image of Jupiter that I prepared just to kind of get this point across. But here's how this works. Take your smoothing function, for the sake of argument with an average. At every pixel, you average the pixels around it. So this pixel color will become the average of all of its neighbors. Okay, and you do that for every single pixel. That will smooth the image. But here's the trick. You then take that smooth image and you subtract it from the original. And what you'll get is you'll get the details that got smoothed over. Which is really interesting, right? When you think of it, like, take the, like, literally blur the image a little bit or smooth it over, subtract from the original, and you'll get the parts that were smoothed over. And then here's what they do. They do the same thing again, but this time instead of looking at the nearest neighbors, you increase the length by 1. So now the average of this pixel for the second layer is going to be these pixels around it. That's the average color. It's the average of all these. And then you do it again, and then you get another image with even a little bit more details, with different details. So the fine details, you get those medium details. And then you do it again. Do it again, and you do it by 1 pixel in between, 2 pixels, 4 pixels, 8 pixels. You do it for how many layers you get. And you'll get these detailed layers, they call them, where they reveal the details of the surface. So you do it 1 pixel, you get this level of detail, and this level of detail, and this level of detail. And once you've extracted those planetary details, it's really easy to extract them. You literally just multiply these and then add them all back together, and you have a sharpened image. It's working on literally different details of the planetary surface. It's amazing. It's awesome. It is freaking fantastic. It is so fantastic, I want to show you guys what it looks like. So let me do another share here. Okay, so right here, let's enable it. This is the atro wavelet transform. So as we increase the small details, you can see the details coming out. These are the small details, these are the medium details, and these are the large details of the image. Let's zoom in a little bit. Now there's 2 problems with this algorithm. The first one is it really sharpens things up a lot. Just look at the difference there, right? Like just look how much details you can get here. But there's 2 problems with this algorithm. The first one is it introduces noise. You cannot add information that's not there. You just can't. And the other thing too is it has this ringing effect. So we have to do 2 additional algorithms to get around that ringing. The first thing we do is you can call this. That will just get rid of the rings nice and easy. And then we have to run a noise reduction algorithm on it. Get rid of all the speckles and all those dots. The common noise reduction algorithm is something called bilinear interpolation. It's basically a 3-dimensional. It's basically a 3-dimensional Gaussian blur, which looks at both how far apart on 1 dimension, looks at how far apart the pixel is. On the 2nd dimension, it looks at how close they are in color, and that way you can blur while still doing edges. That's not a built-in filter. I had to write that one as well. But you can kind of play with these until you can get something which looks nice. This is actually starting to look like Saturn, right? Not quite, not fully. Let's go ahead and do that. But we can just kind of play with these sliders. Might bring down the details just a little bit here until we can get something which looks a little presentable. Okay. By the way, notice how you get that color fringing, those blues and those reds. That's the next thing. Anyway, what does this look like in code to implement something like this? So what's the code for this look like? Well, you're gonna look, I'm about to show you. Okay, so basically this is the HRO algorithm. I'm not using an average, I'm using what they call a B-spline function. But basically, if anyone here has ever taken image processing, you know what an image kernel is or a compilation is, this is my compilation kernel. But basically, the center pixel gets this much weight, 9 divided by 64. The pixels above it will get this. Pixels around here will get this much. And you basically times each pixel around that by this value, and then you add everything together. It all adds up to 1, and that will be the value for that pixel. And you do that for every pixel across.
Is that convolution kernel published somewhere? Or did you,
I got this from a paper.
Yeah.
I got this from a paper on it describing how Hubble did this. But you know, really common ones like if I wanted to just this is a really simple one. This is the average. So if I wanted to do an average where I just average the 9 neighbors next to it, it would just be this. You would just literally times the center pixel and the pixels around it by 9, add them all together, and boom, you have an average, right? This is a really common one. This is linear interpolation. This is another really common smoothing function. Another really common smoothing function is a Gaussian distribution. It's, for those that don't know, Gaussian distribution is basically a bell curve. So you do a bell curve, you know, with your center being the center pixel and the weights around it. But the one that NASA likes is this B-spline. And so that's what I stole. And then it's really simple from that. We basically, we take our scale, we have scale 0, 1, 2, 3, 4. We figure out our stride, which is just a simple power. And then we just basically get, we get our weight from here. We sample based off of what our stride is. Are we looking at the pixel above, the pixel below? The stride will basically insert the zeros for us. And then we return it, and that's our trills. That is how we do that initial scale. And then how that basically works from here is we have our tro kernel, that's the kernel I just showed you, which does the smoothing, our add, our difference, our multiply kernels. And it's pretty simple. We choose how many scale levels we want to pull out. In this case, I'm doing 3 levels of planetary scale. We create a smoothed image. We calculate the difference. And we multiply it by whatever sharpening bias we want to do. And we append it. And then we add it all together. And that creates that sharpening effect that you just saw. Any questions?
Can't remember, but isn't there a metal performance shader for doing convolution?
There is. The CoreImage actually has a built-in convolution filter. The problem with it is it can't, because I can't do it like if you go back to this image. There's one, and my first version of this actually is this way. Here's the problem with the built-in metal convolution. I can't speak right now. Is I'll show you. Is what it cannot do is it can't insert. It can't like it's really good at looking at pixels near it.
Oh,
It
it
can't
can't.
insert it in these.
It can't go out far.
It can't go out further, like, which is what we need to do in order to capture that planetary detail. Okay. Any questions before I go on to the third and final algorithm? Okay. The last one is this. You get that color fringing, where literally because the atmosphere is refracting things here, blue light is traveling slower than the red light. And you get this color fringing. And like this is actually a really simple algorithm. All you do is you calculate how much you need to transform the red channel or the blue channel. You just apply simple translation on the red channel, blue channel, etc. And you can tell you line things together. So it's a really, really, really simple algorithm. So let's go back into my code. Here, first of all, I'll show you what that looks like. So you'll see here, do you guys see how the edges here, you have that red and that blue tinge? So to adjust that, we just move it down here. So you can see we need to move the red channel up. So just to make it really obvious, if we, oh, I got to enable it first. See how we can move the red channel up or down? So basically just move that down, the red channel up until it's all converged.
3D glasses.
I know, right? We do the same on the blue channel. Which is the green channel of it, and there you go. We got rid of that color fringing. And then just because, you know, we want to make this look a little bit better, we can do some just kind of more general, like common stuff. thing. We should almost always do the color balance because again, the color's off here. Usually that means we like to increase the red. I want to lower the blue a little bit. Do just the green. And there you go. We have a pretty decent picture of Saturn. Is that as good as what Andrew McCarthy is doing? No. He also has a telescope that's about 4 times bigger than mine, so you know. He was comparing.
And he's also in Arizona.
He's also in Arizona and not Seattle, that's the thing. Like, if you want to take pictures of anything in the sky, you want clear, dry climates where the air doesn't change or shift much. That is not a coastal city called Seattle.
Also on top of the mountain helps.
Let me see
Was
this.
this
Yep.
from Seattle?
What?
Was this from Seattle?
Yeah, this was from my backyard. This is from everything I do is from my backyard in Ballard, which is neighborhood, just like 5 minutes north of, 5-10 minutes north of
Have you not-
Seattle.
Wanted to like go out into the, go on the other side of the mountains or something?
Oh, I would love to. I'm actually this close to asking my wife to let me buy property. There's this village called the Astronomical, not to put pressure on her, but there's this village called the Goldendale Astronomical Sky Village, where literally a bunch of astronomers bought this big property and they like
subdivided and they
have subdivided and they put all the stuff to like, they put power there, they put internet there. It's out in the middle of freaking nowhere. It's on the other side of the mountain, so you don't have the weather. They sell plots for $5,000 a piece. I can go there, set up a tent, set up a trailer.
Is this in
Stand under the
Washington
stars, take
State?
things. Yeah, it's in Washington. It's about 3.5 hours.
There's a bunch
from
of them,
Seattle.
actually.
Yeah,
Because there's a bunch in Arizona too.
yeah. If I didn't have young kids, I probably would have done it by now. I want to show you guys one more quick thing, and then I have some closing thoughts. So, I want to show you Jupiter. This is not my image. I wish it was, but this is what's taken from a telescope, much bigger than mine, and using some fancier equipment. And I just want to show you kind of how my software performs with something like Jupiter, so you can bring up the details there. And already, like I want to show you Jupiter because I think like better source actually shows the power of these algorithms, right? So we go from this. This is about as good as you can get with just lucky imaging. You will not get a better photo unless you go to like these wavelet transforms. So you can get that. You can bring out kind of medium details. You can bring out kind of large details, and you can see that you can get a really clear, amazing photo. You can do noise reduction there. Oh, I gotta bring these-
Yeah, I was gonna say, is that IO or what is that?
I don't know, about Ganymede, I think, one of those, something like that, but yeah. It's probably what is the anyway, I won't spend too much just thing, but you can like do some seriously powerful stuff with these algorithms, right? Anyway, going back to any questions before I put in my closing thoughts? So, let me just go through my last few slides here. So, what about the moon? Can you do these on the moon? And the answer is yes. Every lunar photographer uses these same wavelet transforms, the same things to create really high, crisp, clear things of the moon. And I actually had a coworker ask me, why don't you turn this into an app? Point your phone at the moon, zoom in, take a picture that takes like 30, 40 frames, stack them together, create a nice machine learning algorithm that maybe figures out what the wavelet transform should look like. And then you can take these amazing, highly detailed pictures of the moon. And like, here's a good example of what that could look like. Like you just take your phone, you zoom into the moon, you take a picture of it, you stack it, you use your machine learning algorithms to run the wavelet transforms, and you get this amazing clear picture of the moon. And for anyone who hasn't picked up on where I'm going on with this, you'll then have the birds tell you you're taking your photos of the moon. Now, I don't know if that's what Samsung is doing or not. I honestly don't know. But I think you could. I think that you could create some amazing apps here that do some easy stuff here. That's my presentation. Have some questions? Just thoughts?
Are you asking one of us to show off to you right here?
Go for it. Go for it, man. I would love to have a good planetary astrophotography processing suite on the Mac. Like, I want it so much that I wrote my own freaking own. Like, this is not easy. I had to like get knee deep in like all these research papers and rereading source of open source projects. Like, this was, And the reason why I did this is because like you literally cannot run any of the stuff on the Mac. You can on Intel Macs, but not on Apple Silicon. It's just like, anyway.
How far would you say your app is now from the ones people are using on Windows?
So, It's hard to say, but I will say that, because I haven't tested all of them. I've tested two, because I do have a gaming PC, right? And I was able to, so I did load that too, I did compare it. And for my images, my stuff outperforms. But the problem is like, I'm also kind of developing off of my own stuff, right? So I'm tweaking variables based off of the results I get from my own stuff. So it's hard for me to share. And there's also stuff that there's also a lot of stuff I'm missing. Like I just went over the three I've implemented. There's a whole bunch more stuff you can do to get these really high quality things I just haven't gone yet. And there's also like there's what they call surface photography, which is where you take highly detailed pictures of like surface, so individual craters on the moon, and like individual like sun flares, and just super high detail that my stuff isn't doing. And yeah, but anyway, that's a long answer to the answer. Like for the algorithms I've implemented, and from the two I compared, and for my stuff I've tested, I either exceed or I beat what the PC stuff is doing.
You led with how you can't use the same camera for planets that you use for nebulas and galaxies.
That's correct.
Why is that?
Two reasons. I mean, whether you can't, like, let me just step back and say, you absolutely can, but should you know? And the reason why you shouldn't is because you're trying to capture two different things. When you're taking a picture of a nebula, when you're taking a picture of a nebula, you don't have light to work with. It's just not there. You're literally scraping a few photons a second. So what you want is you want something really fast, and also you want something with really big pixels. Like, cameras with really big pixels basically gather better light. It's easier for them to gather faint light. This is one of the reasons why like full-frame cameras tend to outperform other cameras when it comes to low light situations, because they have bigger pixels. The other thing you want is high frame rate, because anyway, the other thing is you don't care about frame rate, because with space dust, you're just literally taking long exposures. Like the exposures of the pictures I've taken, they're usually what I do is I do exposures of like 4 or 5 minutes. And I'll do like 10 hours of them stacked together, right? Now let's talk about with planets. Planets, you want small pixels, because small pixels give you better, like with planets, you just want to zoom in as much as possible. Big pixel, and long story short, small pixels have a much more zoomed in effect, right? The iPhone has a tiny sensor, but they say it's a 35 equivalent focal length compared to full frame. The way they achieve that is they just make the pixel smaller, and so you get the more zoomed in effect. And the other things want high frame rate. And so a planetary camera will tend to have really small pixels for really zoomed in rate. They will also tend to be really fast, because you have so much light to work with, you're just trying to gather frames, and so you're just trying to capture the fastest video you can get with the smallest pixels you can get. Where with space dust, you're basically trying to get the longest exposure you can get with the biggest pixels you can.
So with some of these high dynamic range cameras, are you capturing more than just RGB? Are you sampling colors at different spacings, or pretty much everything in RGB?
Oh man,
RGB sensor?
yeah, no, that's a big question that can take lots of different places. To really quickly, really quickly, I can't quickly summarize. I will say this: there's two types of there's lots of different types of astrophotography out there. One you get is you can get into things like where you're photographing galaxies and nebula and things like X-ray and infrared and some of those wavelengths, and those require specialized cameras which are sensitive to those wavelengths. And by the way, if you ever want to see an amazing picture, look up the Andromeda Galaxy in infrared. It is mind-blowing. Like, it is one of my favorite, it is such a cool picture. But anyway, the other type of picture you have is what they call narrowband. And the basic idea is that when you look at space dust, so think of the universe, right? Think of what space dust is. It's where stars are forming. They're basically big piles of hydrogen, oxygen, and sulfur. Those are those are the abundant elements in nebula. And so when you look at the light that hydrogen and sulfur and oxygen actually transmit and reflect, they're just these tiny slivers of the wavelength. A tiny section of the red, a tiny section of blue-green, and and a tiny section kind of in between. And so what you can do is if you know, if that's all you care about and you want to get away from like city light pollution or all the stuff like that, then you just basically get these filters which just capture those little narrows of light that hydrogen, sulfur, and oxygen capture, and then you can take some really amazing, and then and then basically you get a lot better signal, you get a lot clearer images, and you can actually do some really cool things with color. You can create these, what they call false color images. It's actually how Hubble made space photography popular. So they would do these false color images using these specialized filters.
I think most popular, like when NASA releases a new image, they're taking the James Webb telescopes. I think they're usually false color.
Yeah.
Because, I mean, some of them are infrared or something like
The
that.
the natural against this is a very controversial question in astrophotography. What is the true color of these things, right? And the reason why it's controversial is because our eyes, they don't pick up the light that hydrogen emits. Like we only pick up about 30% of the wavelength that hydrogen emits, and most of the stuff is hydrogen, right? And so most of the stuff is just invisible to our eyes. So if you wanted to say like, the other thing too is like, fact of the matter is if you were to actually visit these guys, if you actually take a little spaceship to one of these nebulas and look at it, you would just see a gray cloud, right? That's all you'd see is a gray cloud. Why would you see a gray cloud? Because there's just not a lot of light there. Think about when you're in a really dark room with just a little tiny light. Everything's gray. You don't see colors when you don't have a lot of light. That's just how our eyes work. If there's no light, there's no color. Now let's say you were able to. Now let's say like you were able to somehow shine a giant flashlight on these things so you could see the colors. Well, the colors you would see, it would depend a lot on the object. But for the most part, they'd be a kind of a reddish hue, a pinkish reddish hue with some specks of green and blue. That's kind of the natural color of those.
Are you saying because things are mostly iron or
But
something?
because most things are hydrogen, and hydrogen is red.
Okay. Do you use filters on any of your stuff or
Some things. Let's go back like here. If you want,
on the actual,
yeah.
on the camera filters, like physical filters?
Like here's some.
Oh, that's not
You're on the
sharing.
other screen.
Oh, let me show you this right here. Share screen here, right here. Here's some photos I took. This is Seven Sisters, Pleiades. It's near Orion. This is no filters. This is a natural color. Like if you were to visit this thing and shine light on it, you would see this blue thing. You would see this color blue. This also is no filters. This one is no filters, but what I did do is I stretched the colors to make them, and I adjusted the hue and saturation up to bring out the blues more, because I think this color looks cool with the blues. That's an artistic thing. This photo I purposely made orange because I took it for Halloween. I applied a green curve. You can see how the black is all green, because I thought it was spooky and more Halloween-y. This is the definition of a false color photo. This thing I literally took 3 different wavelengths. The green and the blue channel were actually 2 different shades of red that I made green and blue to make it look cooler, right? This is another false color because I wanted to make it look like Siri as a joke. This is natural color. That's the natural color of the Milky Way. I took this over Bear Lake. That's a whirlpool galaxy. This is also natural color. No really like modifications. Fun fact about this photo is you see that little spot right there? That is a nebula. Sorry, a supernova. So what happened was I took this photo of this thing, and then about 6 hours after I took this photo, by pure coincidence, a supernova happened. So I took another one, and you can see the difference right there.
And you
That's
caused
awesome.
that?
What?
You caused that?
Yeah.
Exploding those stars.
No, it was
happened
just,
like how
Can you just make a-
thousands of years ago?
yeah, but like just literally about 6 hours after I took this photo, a star supernovaed, and so I took another photo the next night.
Oh, so you heard that?
Yeah,
that there was a
I took a picture of this thing, and then because I follow on my Twitter or X, I follow a whole bunch of astrophotographers, and when when a supernova happens, everyone's like, oh my gosh, a supernova, take a picture. And so, the next dark night, I went and took another picture, and, you can see it from this tiny little speck of a star to that exploding right there.
How long did the supernova last, like, that you could see it like that?
A few months. If you did that big, what? I mean, it depends on the supernova, and it's very variable, and it'll go kind of up and down a little bit as, gases collapse and everything. But this one was visible in telescopes. Like you could actually see this one in a telescope. It was just basically a little faint star. You could still see it in a telescope, and it was visible for about like 2-3 months in telescopes.
You should just make a supernova filter for your app. Just make one wherever you want. That should be easy.
This would be a more natural. This is a more natural color than this. This is the Crescent Nebula, and it's kind of like this reddish pinkish hue. Like if you were to visit this and shine a giant, because there's not a lot of sulfur going on here. There's not a lot of oxygen. It's mostly hydrogen. If you were to fly your little spaceship here and put a giant spotlight on this thing, it would look like this.
Is Doppler shift a thing?
Yeah.
Okay.
Redshift.
How good is your telescope?
I mean, I know Doppler shift exists with astronomical objects, but I'm wondering, if you look at that and say, well, this is the color it actually is, if it's being shifted by.
That's why James Webb is, James Webb is focused more on the infrared spectrum because of they call it redshift, as things are getting further away. Then basically to look back further in time, you have to go more and more shifted. But
Yeah.
maybe there's more.
Anyway, I'm starting to get into some of my photographs I'm more embarrassed about. There's a comment. That's cool.
Why are you embarrassed about these?
This is kind of my early days when I'm still figuring
Yeah,
stuff out.
but we're comparing them to the photos we've taken, which
With our phones.
Yeah. That was my first attempt at taking pictures of Certain Nebula. Anyway, yeah. That's my birthday today.
Great.